Morning everyone! We are going to present our research entitled A Short-Term Load Forecasting Algorithm Using Support Vector Regression and Artificial Neural Network. I am Ms. Shire Sarabia, and my group mates are Mr. Abad and Mr. Yuzon. Our thesis advisor is Dr. Michael Passes. Our research is about electric load forecasting. It is the science of predicting the most economical amount of electrical power to be supplied by electric utility companies. Load forecasting is important when it comes to producing the maximum efficiency of operations of these electrical utility companies. It also helps minimize the amount of power loss in the system. Support vector machine. It is proved to have a good pre-processing performance due to its quadratic programming and good learning ability even with small sample set. It also solves the weak points of ANN such as overlearning and overdepending on experience. Artificial neural network. It is a network system that contains numerous fully interconnected, simple processing elements. ANN draws a link between the input data and the output data, rather than just relying on mathematical functions such as SVR. Statement of the problem. Large gap between the supply and demand could lead to shortage or surplus in power supply. The main objective of this study is to develop an automated algorithm for short-term load forecasting using support vector regression for pre-processing data and artificial neural network for load forecasting. Specific objectives: 1. To gather test data for analysis. 2. To develop an SVR-ANN algorithm for pre-processing and load forecasting. 3. To develop a separate ANN and SVR forecasting algorithm for comparison purposes. 4. To validate program outputs using statistical treatment and obtain a percentage error of less than 5%. And lastly, number 5, to make a comparison table containing the SVR-ANN and SVR-ANN test results. Significance of the study. This study helped minimize the gap between the demand and supply of power to avoid shortage or surplus in power supply. It also aided the unending needs of consumer, though given minimal and limited sources of electrical energy.
Next would be the SVR-ANN process. At first, we again download the data from the NGCP website, and then we set the parameters or initialize the parameters such as time, day of the week, time of the day, holidays, and load value yesterday. And then we program an SVR-ANN algorithm for pre-processing and forecasting loads. And then the downloaded data from the NGCP would be uploaded to the prepared algorithm and to be set for parameters and training. So next, we select the activation and kernel function such as ReLU and RBF. And again, by trial and error, we try to find the best numbers or the best parameters for the hidden layers, the epochs, seed for ANN, and obtain the gamma and C function for the SVR. And again, we try to run the program, forecast the power load, and compute for the errors. Again, if the MAPE is less than 5%, we end the simulation. If not, we change the ANN and SVR parameters again. For the demonstration, first off, open the command prompt and type main.py to run the program. Next is to click Upload Dataset and upload the file downloaded from the NGCP, which is the rdemand.csv. Next is to input parameters. Click Train and Test Model. Now we wait for a few minutes. The MAE, MAPE, and the time elapsed will be displayed at the bottom of the user interface. Now, access the directory folder, output, and look for the most recent trial. It comes up with a folder name of the date and number stamp. Open ANN SVR plot.png to see the histogram and scatter plot. And then open ANN SVR test set predicts.csv to see the forecasted results.
We have here the 3-week sample results using the support vector regression algorithm. So we have here the yesterday's actual load, today's actual load, and the SVR forecasted load, which are all in megawatts. So we have here the forecasted load, which is obtained or trained using this yesterday actual load. This today actual load, when compared to the SVR forecasted load, seems to be very near with each other. So it seems that our forecasted algorithm, our output load has a good correlation with the input load, or the actual load in megawatts. So this is the sample 3-week forecasted load using ANN algorithm. So like for the support vector regression, we have here the yesterday actual load, today's actual load, and forecasted load in megawatts. This also shows a good correlation between the input and output data, since our forecasted load seems good or near to the today's actual load from the NGCP site. So for SVR-ANN process, we have the same parameters used as the ANN alone and SVR alone processes. The only difference is that for the SVR part, we have subdivided the loads for low, medium, and high loads. We set gamma and kernel for high loads, for medium load, and for the low loads. So first, let's talk about the artificial neural network parameters. For the number of neurons in hidden layer, we used 500 in the first layer, 200 in the second layer. We still use the rectified linear unit function, or ReLU, for hidden layer activation function. We used 100 epochs and 16 seed for the best fit. For the SVR part, we used the kernel function for low, medium, and high load as the radial basis function, or RBF. For the gamma of the 3 subsets of our load, we use 0.00368, and for the C parameter, we use 47,000 for high load, 49,000 for medium load, and 50,000 for low load for the best fit of our trial in SVR-ANN. Upon training and testing this model, we gather 175.6893 megawatt as our mean absolute error, which corresponds to 2.47% of mean absolute percentage error. So this table, a 3-week sample results using SVR-ANN algorithm, still has the yesterday's actual load, today's actual load, and SVR-ANN forecast load in megawatts. From the today's actual load and SVR-ANN forecasted load, it seems that it has better correlation than the other two, or the first two trials we had, which are the SVR and ANN. There are very little differences from the forecasted load and today's actual load. Using the formula, we will get the mean absolute error by getting the summation of all the load differences between the predicted load and the actual load, wherein the first one is a prediction load error of 167.8359 megawatts. We're going to add those errors until the last one, which is 5.0475 megawatts, and then divide it by the number of data points we have. With this, we will gain a mean absolute error of 175.6893 megawatts, which is the sample trial for support vector regression and artificial neural network algorithm. We will again use the formula of the summation of the load percentage error of all the trials or all the data points, and then divide it by the number of our data points. So for our first load error, we have 3.0284%. We're going to add up all those percentage errors up to the last point, which is 0.0612%, and then divide by the number of data or number of data points we have. So with that load errors, we will gain a mean absolute percentage error of 2.4694% for the whole data that we have. For the 4-year data set we gained from the NGCP. To compare the three results or the three algorithms, we have here the comparison or the bar graph as our comparison chart. So the blue bars correspond to the actual load, orange bars for the artificial neural network forecasted load, gray bars for support vector regression forecasted load, and the golden bar for SVR-ANN forecasted load. So these standard icons above shows that the SVR-ANN is the nearest forecasted load to our actual load. So our first, second, fourth, fifth, sixth, 14th, 18th, 19th, and 20th points, which correspond to the days in our 3-week sample results in our previous tables. So those points correspond to the points where SVR-ANN is the nearest point to the actual load, or it shows the best prediction or the best forecasted load among the three, among ANN, SVR, and SVR-ANN algorithms.
For the comparison of results, as you can see from the table, the SVR-ANN algorithm yielded the best MAE and MAPE results, with a MAE of 175.69 megawatts and MAPE of 2.47%. For the conclusion, we have here a table for the objective and its corresponding conclusion. For objective number 1, to gather test data for analysis, actual load data from year 2015 to 2019 were obtained from the NGCP site. Number 2, to develop an SVR-ANN algorithm for pre-processing and load forecasting. An SVR-ANN algorithm for pre-processing and load forecasting was programmed using Python. Third, to develop a separate ANN and SVR forecasting algorithms for comparison purposes. Individual SVR and ANN algorithm for load forecasting was programmed using Python. Fourth, to validate program outputs using statistical treatment and obtain a percentage error of less than 5%. The SVR-ANN algorithm yielded a MAPE of 2.47% and MAE of 175.6893 megawatts. And lastly, to make a comparison table containing the SVR-ANN and SVR-ANN test results. The comparison of the forecasting results of the three models showed that the SVR-ANN yielded the best performance amongst the three.